Hello, 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 everybody, and welcome back. In this video, we are up to question number 5 on the Ontario Senior Math paper from 1968. A piece of wire 10 feet long. Oh yeah, this is back when Canada used feet. That's kind of cool. Anyways, is divided into two portions, which are then bent to form a square and an equilateral triangle. And this is a classic calculus problem. If you don't run into it in your high school calculus class, assuming you still have one, you will likely see it in first year calculus. We give this one out basically every other year on our introductory calc course finals or midterms. Anyway. So bent to form a square and an equilateral triangle. Sometimes, it's just about shapes. I've seen it with triangle and circle. I've seen it with circle and square. You can make it anything. If you want regular hexagon and rectangle whose length is twice its width, you can do that. There's lots of ways to do this sort of a question. It's the same process, it's just a slightly different equation for setting up. Now, let me read the rest of the question to make sure I know what I'm talking about. Find how much wire should be used to form the square so that the total area is a minimum. Yeah, it's an optimization problem. And I don't think we'll actually have to use calculus, but I'm going to. I'm going to use calculus here. Give your answer in decimal form to 2 decimals. Yikes. Okay, so we're actually going to have to do some decimal calculation, and I said in the very first video we are putting that calculator away. They didn't have them, so we don't get to use them. Okay, so let's sort of visualize. We've got this wire here, 10 feet long. I'm going to secretly pretend it's meters, but 10 feet long. Basically, we cut it at some point, and that splits it up into x, and what's left over is 10 minus x feet. And we take this x bit here and we bend it into a square. So the wire becomes the perimeter of the square, and so the sides of the square, well, there's 4 sides, all the sides are the same length, so we get a wire square of side length x over 4. Okay? And the rest of this turns into an equilateral triangle, the sides of which you can work out because they're all the same. And there we go. Now, I put the x with the square because that's the one we're asked about. Find how much wire is used to form the square. If they were asking how much wire is used to form the triangle would get the x and the square would get the leftover bit. Because I want to solve for this value x. That's what we're interested in. Solve for the value of x that minimizes the areas here. Okay. So, what can we do? Well, they want to talk about the areas of the squares, or of the figures. So the area of the square is going to be x squared, or x over 4 squared, x squared over 16. Area of an equilateral triangle, in terms of its side length, is not something that is the most common. But it's root 3 s squared over 4, where s is the side length. So we'll have 10 minus x over 3 squared times root 3 over 4. And that will be root 3, 10 minus x squared. The 3 comes out squared. This is 9 times 4, 36. Okay. Just as a side note, in case you ever do a calculus question like this, if you've got a length of wire w, and you do x and w minus x, the shapes that you make, the areas are always going to be some constant value times x squared and some constant value times w minus x squared. Depending on the shape, a could be 1/16, which is what we've got over here, and b could be root 3 over 36, but this is always how it goes. Okay, the geometric shapes you make will always be something in terms of x squared and the w minus x squared. Okay, but what have we got? So x squared over 16. I'd like to get a common denominator here. If I can. Common denominator, 36, so I need a factor of 9, so definitely need to multiply 16 by 9. 144 should do it. Yeah, so multiply this base here by 4. we'll get 9x squared plus 4 root 3, 10 minus x squared, 144. Okay, so I want this to be minimum. Okay, and I said I'd do it with calculus. I will do it with calculus. I just like to briefly point out that you don't have to use calculus if you don't know calculus. This is actually one that can be solved using regular old high school math that we have nowadays. Basically, all you need to realize is this top bit will turn into a parabola, an upward-facing parabola, and you just need to find the value of x that minimizes it. Okay, and there will only be one. So you expand this top bit out. You don't even need the 144, and you just find the x-coordinate of the vertex. That'll do it, and it'll have to be the minimum. And this expression here is the sum of the areas. So that's how you minimize the total area. But I'm going to use some calculus. So we want to minimize this. So we'll say it's enough to minimize the top, because the bottom's just a constant. It's not going anywhere. Let's actually expand it out. Yeah, we should probably expand it. Should we? No. Well, I'll keep it away. Keep it as it is, just for now. Okay. So we want to minimize that. How do you minimize things? Using calculus, you take the derivative to find critical points. Okay. So we could give this a name, call this function a of x for area. So derive it, so you'll get 18x plus 8 root 3, 10 minus x, and don't forget you got to do the derivative of the inside. Derivative of 10 minus x, 10 goes away, but the derivative of negative x is negative 1. Okay, and we need to find critical points. There will only be one. So we set this whole thing equal to 0. 18x minus 8 root 3 times 10 minus x. So 18x minus 8 root 3x. Oh, sorry, plus 8 root 3x minus 80 root 3. So 80 root 3 divided by 18 plus 8 root 3 is x. This is the only one, although I would guess, like any actual calculus problem, you can't just say, well, that must be the value of x that works. Also, we can divide top and bottom by at least 2. Okay, you want to justify why this is the minimum value. Here's another place where you could use that argument that, hey, a is a parabola, so this is the minimum. You could also do something like take the second derivative and show that that's always positive. What is the second derivative? It'll be 18, and then it'll be plus 8 root 3, which is always positive. So the thing's always concave up, and you're only going to get sort of the one minimum value using what do they call it? Second derivative test for maxes and mins. Anyway, however you want to do it, point out that the whole thing's a parabola and it's got a minimum. Use a second derivative and got a minimum. You can see that this x is the only value. The reason I'm doing it this way rather than another way you might know if you know calculus, which is to say, all right, your critical points are the endpoints, so the lowest and the smallest and biggest possible values of x along that wire. And remember, if we go back to it, the value of x is at most 0. You chop off none of the wire, and it's at most 10. The square gets all of it. Okay? So you might feel compelled to do a little bit of what you were trained in calculus and test all three, plug them all into the a of x function, the area function. But this one's going to be a nightmare to figure out that area and compare it to the others. So I'm telling you, just use the geometry or use the second derivative and say, this must give the minimum. Okay, so there we go. I want 40 root 3 over 9 plus 4 root 3 is wire given to the square. But here's where it's a little tricky. They said give your answer in decimal form to 2 decimals. Uh-oh. We don't get a calculator, so what are we to do? What are we going to do? Well, I suppose we had better figure out things. Now, I'm confident you could probably say square root of 3 is 1.73. It's 2 after that, isn't it? So I'm not going to worry about doing square roots by hand. I'm going to see right now, actually, if I can remember how to do it off the top of my head. I know it's pairs of zeros, pairs of zeros. 1 goes into 3 once, and then you multiply it out, and then you get 2, bring down the zeros. And then you have to think, what's the... So to get the next digit, you have to consider these two at the same time. Now, I know it should be 7, but why is it 7? 7, you choose the 7, so it's 1.7 times, so 1.7 times 7 is as big as possible. So 17 times 7 is 9, carry the 4, 119. If I did 18 and 8, it would be 4, carry the 6, and it'd be 144. No, I'm missing something. And I can't figure out what that something is. If I'd read the question ahead of time, I would have prepared my square roots by hand. And maybe that's something I should teach you guys to do so that I can remember how to do them. But I don't remember how to do square roots off the top of my head by hand. I know you can do it. It's been shown to me, but I don't remember it. But I do know square root of 3 enough. And this is a common value. I don't know the digit after this. I would guess a 9, and I would probably guess wrong, because it's a 1 out of 10 chance. Just let me think for a second, see if I can salvage this square root of 3. I know it should be a 7, but why is it a 7? Do I not do the subtraction? I thought you did the subtraction. It's this value, and then it squared plus 2 times the 7 times the 1. I think you ignore decimals. So 49 plus 2 times 70 is 189. And the next one wouldn't work. 64 plus 2 times 80 would be more than 200. There we go. That's the trick to it, I think. So you get a 7 there. And then you'd say, okay, you subtract off that 189, and you're left with 1, 1, and you bring down the next 2 zeros. And then you ask yourself, what b goes here so that b squared plus 170b, 2 times 170b, is less than, is the biggest b so that this relationship holds. That should be it. And so another way to write that is 340 plus whatever b I choose times b needs to be less than 111. So for example, if I pick b as 2, 342 times 2, you got the 4 there, the 8 there, the 6 there, 684, certainly less. If I choose 3, we get the 9, nothing to carry, 2, something to carry, and so we get 1029. But if I were to choose 344, 6 something to carry, 6, so 7 something to carry. You'd be in the 113s, and that's more than the 1100 here. So yeah, there we go. It just took a little while of thinking. Obviously, if I lived in, so 3 is the number I want. So it was 1029, and the difference there is 71. Now we bring down the next 2 zeros, and we ask that question again. What b do I put here so that 173 times 2, so that would be 346 plus b times b is less than 7100. Okay, and I'm saying that that's going to be 2, based on my recollection of how the number works. So 349 times 3, 7, 2, 4, 1. Don't like that because that seems to be less than what I've got here. So if I missed something again, quite possibly. Quite possibly. Or maybe I don't remember square root of 3 as well as I think I do. Because it looks like we've got a lot of room for improvement there. And I don't like that. Oh, right, it's a 0 here. That's my issue. You got to treat this as the 0, and then you're adding on the b. Okay, there we go. Because that's what I was doing with the other ones. Okay, I was wondering, because it was going to be way, 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 way too small. I always forget. So it's 370, and the b is the new digit we're trying to find. So we got a little placeholder there. So 3463 times 3, and you can already see 3 times 3 is going to be in the 9,000s at least, so that's not going to work. And so 2 is the best one for you. So that'll be 3462 times 2. That'll be 4296. 6924. We'll get a difference of 176, and we would bring down the next 2 zeros. So I need b so that 17320 plus b times b. Oh, this thing doubled. Again, I keep forgetting that. That'd be 64. So I need that to be less than 17600. But this is already too big, so the b is going to have to be 0. That'll be my next digit. And so then we come down again. We'll add another 0 here. So eventually these 2 zeros being added on will outpace these zeros. But we can ask the same question. I would guess 17 compared to 3, I'm going to guess around 5. So let's try 5. 346405 times 5. You can see this is working. It's just taking a long time. All right, that works, and we're so close. There's no way 6 is going to work. So the next one is 5, and you can actually double check. This is working. This should be right. I didn't know these two off the top of my head, but I'm confident. And I assure you, if you're watching this video, I've double checked afterwards to make sure I don't look like a fool. And these are the square root. This is the square root of 3. So that's more than enough digits, I think. And we've actually shown how to do it. So square root of 3, we're saying 1.73205. So 4 times the square root of 3. The only reason I'm just getting enough significant digits so that the calculations I'm about to do not backfire on me terribly. So it should be 6. So 6.92820-ish. The last digit, the last 2 digits might be a bit iffy, but they asked us to 2 decimal places, so you can see I've got more than enough of a buffer here in case I'm rounding significant digits or things like that. So that's 4 root 3, 40 root 3, which is the top thing, should just be 69.2320. So we want to, and 9 plus 4 root 3 should then be 9 plus 6 is 15. Okay, so now it's just sort of a decimal long division. 92820. 69.2820. All right, 16 goes into 73 times. So we'll get 0. Actually, the 0 should be over here. 0, 6, 4, carry the 2. 8, 7, carry the 2. 17, carry the 1, 4. We'll borrow here. 4, 7, 9, 4, 1. Three times 1, this should be 45, it's 47. Why am I getting a 22? 4 times 17 goes, because 16 goes into 74 times 16. 17 goes into 68, and 68 is bigger. That's my mistake. This is what happens when it takes you a long time to do these sorts of calculations. It's been a long time since I had to do something with long division. 2820. There we go. Okay, 0, 8, 2, carry the 3. 1, carry the 1. 7, carry the 3. 23, carry the 2. 6, there we go. So 6, no, 2, 9, 6, 5, and we got another 5 here. All right, so it's 4 point something. Great, we just need to do 2 more divisions. How many times does 16 go into 55? 48's the closest, so we're going to say 3 times. And we know it's 4.7 something. 0, 6, 4, carry the 2. It was an 8. And then a 7, carry the 2. The 7, and then carry the 1. Yeah, there we go. So our previous calculation wasn't, I guess, all bad. I'm going to ignore those. Get rid of 8 there. So 8, 0, 9, 7, so 0.7, 9, 0, 8. All right, how many times does 15 go into 79? Well, 15 goes into 75. Actually, no. 16, round this up, goes into 85 times. So I'm tempted to say it's a 5, but it might be a 4. Let's find out. So 0, 0, carry the... I'm just going to get rid of those. Carry the 1. 41, carry the 4. 14, carry the 1. 46, carry the 4. 29, carry the 2. So it looks like it's just a little too big, so it's going to have to be 4. And I could probably stop there, but I'm gonna do the long division in its entirety. We already know what 4 does, so we get 8, 2, 1, 7, 3, 6, 7, 3, 5, 1. So just under. And then we bring down more digits if we needed to. But there we go. So actually, not a whole lot of time was spent on the calculus part of this. That was easy. For me, the hard part was doing this sort of long division stuff here and finding the square root by hand. So that's kind of interesting to see how things change. With a calculator, without a calculator, I struggled to do the sort of calculations you were expected to do back in 1960. I don't know how hard they expected them to be, but I imagine students were a bit more comfortable with these sorts of calculations there. So now the only question here really is, do I need to do one more digit and then round up? Did they say round? That's the question. When they say to 2 decimals, do they mean round up? Or something like that. So that's, Well, let's compute one more digit. That way I can say confidently that I would know what to do if needed to. So how many times does 16 go into 153? So just less than 10. So it would have to be a 9 here. It almost certainly is a 9 here. Maybe an 8, but either way you're rounding up. But let's get to that digit. So 0 at the very end, 8 carry a 1, 3 carry a 7, 18, so 25 carry a 2, 83 carry the 8, 45 plus 8, 53 carry the 5, and so 1, 4. Yeah, so it'll be a 9, so I guess you could round up. They're not saying rounded to the nearest hundredths place, so I don't know whether or not they would accept them. I mean, I would put 4.34 because those are the first decimals, but I guess rounded is fine as well. I mean, as long as you make it clear you're doing the calculation, you can say, you guys were ambiguous, here are both the possible answers based on my reading of the question, and that would be fine. And the same sort of reasoning applies today. If you explain yourself, you should get the marks. Okay, so that was question 5. A fun little adventure in sort of doing everything by hand. Square roots by hand, which I had to remember, and the long division, which I don't usually get to do. All right, let's take a look at question 6 in the next video, and hopefully that'll be a little less calculation, a little less theorem. I'm already liking the symbols I'm seeing here, but we'll take a look at question 6 next time. Take care.